So hello, everyone. My name is Robert Underwood. I'm a postdoctoral associate at Argon National Laboratory, and today I'm going to be talking about using Dagger to improve the CI portability and performance for a C++ library that we developed there. So first, I wanted to start with a little bit of information about the library that we're working with. So the library we developed is called LibPressio, and it's an interface for over 30 different lossless and lossy data compressions used within the scientific community. It's used for scientific techniques such as crystallography, which studies the fundamental structures of materials. It's used in cosmology, studying the evolution and growth of the universe, climate science, linear algebra, and other scientific domains. It's used fairly widely for a scientific code across 5 different Department of Energy labs, 10 universities, and 2 international supercomputing centers. And it has quite a bit of different kind of components. So what makes CI/CD for LibPressio difficult? Well, the hardest thing about CI/CD for LibPressio is that our dependency looks like this image on the right, which I know is a little bit hard to see, but that's kind of the point. It's kind of a mess. And this doesn't account for things that are common variants. So in the scientific computing community, we frequently have these standard dependencies that have multiple implementations. So we may have multiple implementations of what we call MPI, which is a hardware accelerated communications library. We often have multiple implementations of BLAS, which are hardware accelerated linear algebra libraries. Depending on what platform you're running on, you have different GPU acceleration libraries, and all of those things potentially change the dependency graph that you have for the software you're building. And then on top of that, LibPressio itself, to minimize the difficulty of installing it on various platforms where you may not have support for specific things, it has 30 plus direct optional dependencies that we can potentially turn on and off. LibPressio itself is somewhat large, 25,000 lines of C++ code in its core, and somewhere between 20 to 40,000 additional lines in its extensions. And then there's additional Python, Julia, and Rust code on top of all of that. And both we and our dependencies evolve quickly. Distros seldomly package the newest versions of packages that we use or our users use. And unfortunately, because a lot of the code that we're working with is research code, the ABI and the API of our dependencies change frequently. And we want to catch the breakages that users might experience before they do. So we need to be able to run CI/CD quickly and then catch things when caching may or may not be appropriate. Additionally, we do a fair bit of stuff with our CI/CD. We test right now 5 different Linux distributions with different compilers, different sets of libraries. We occasionally need to support uncommon configurations, such as like really ancient compilers or proprietary vendor compilers, which makes building a little bit weirder as well. We need to support Python's mini Linux build for Python embedded packages. In the HPC community, high performance computing community, there's a widely used package manager called SPAC, and we want to make sure that nothing gets broken with our SPAC installation. We also build Docker containers, and we run approximately 500 unit tests with every configuration. And we want to do more. But depending on what we do, a cold run of our CI/CD can take 30 minutes for a patch release to up to 36 hours for a full LTS release, where we're testing every possible configuration that we have. Other things that are potentially challenges here for LibPressio CI/CD is that every CI/CD system that we potentially need to interact with is different, and they often all use YAML, which I know that YAML being a pain point is something that's fairly common within the Dagger community, but it's definitely a pain point for us as well. Another thing that Dagger doesn't currently have a great answer to, but something that's also important with us, is we also need to often test with specific vendor hardware. This is something that we think could be addressed in the near future. Like we could do it now ourselves by mounting all of the various hardware devices into the container. But we think that there's probably an opportunity there. And then ideally, we'd also want to test other operating systems. But again, that's something that's further on the horizon. But ultimately, the goal is to address as many of the "it worked on my laptop" problems before we're having to iterate on CI/CD, taking up core hours that are allocated to our jobs. So we're not necessarily having to compete as much between CI/CD resources and resources we would use for new scientific experiments that we want to consider. So what did we do before Dagger? We had kind of a poorly performing hodgepodge of things, ranging from a bash script that was in a Travis CI and then was eventually migrated to a set of local Jenkins instances. And I think they want us to migrate again to GitLab. But the point here is we were having pain points of having to port a lot of different things, potentially to different CI systems, as the sites that we run our CI/CD on changed their platforms. So that was a pain point. We're frequently having to test the other Linux distributions we had with Docker files, which we would often forget to update because they were not part of our standard build. And then we would have to run a bunch of by hand tests before we do our LTS releases. And all of this like lack of portability that we had because we were having to deal with how each different CI/CD system did things means that we often didn't implement things like fine-grained caching or fine-grained parallelism in the build. So how does Dagger help with all of this? Well, since we've adopted Dagger, it's improved the portability of our CI/CD pipelines. It's improved the programmability, making it easier to express the kinds of combinatorial verification that we want to use. It's improved our caching story and improved parallelism of our builds. So improved portability, one of the really important things for us in adopting Dagger was that Dagger is open source, Apache 2, and it runs nearly anywhere, which means that we don't have to worry about vendor lock-in and we don't have to worry about our sites potentially changing the CI/CD environment that we're going to run our Dagger pipelines in. It also vastly simplifies the process of bootstrapping new devs because we can just say /run ci/test.py and students on their laptops can verify that, hey, the change that I made to LibPressio is not going to break GCC 4.8.5 or some other thing that they don't even know that they need to test on. It also protects us from what we call cowboy compiles. Some of my colleagues are from the age of Linux and Unix, where if you wanted to install something on your system, you /configured it, you made it, and you made install it. And then you modified your LD library path and all of these other environment variables that kind of pollute everything. So then you can end up in situations where you got like half of version or dependency A's version 1 and half of dependency A's version 2. And with Dagger, because everything's being built in isolation, those kinds of things just don't affect our Dagger-based CI/CD, which dramatically improves our ability to get reproducible error messages from various people. It also makes it very easy to test other operating systems other than just the host operating system. Here I'm using the word OS here a little bit loosely. I really mean more distribution. But again, we hope in the near future to also potentially look at using KVM with Dagger to potentially test other operating systems as well. Additionally, we have improved programmability. I'd already talked a little bit about, yes, indeed, get off my lawn. That's from the chat, by the way. Improved programmability. No more YAML, no more Docker files, no more Groovy. We can write our pipeline in Python, which is something that our my colleagues and students that come and visit the lab all have familiarity with. And it's way easier to implement conditional logic rather than having to say, in YAML, does this system have a GPU? We can do a same thing and test, does this system have a GPU? And then make the right number of decisions there based off CPU cores, memory, that potentially affect how we would potentially build. It's easier to loop over various settings, so we can loop over, say, Fedora 36 and Fedora 37, and we can kind of templatize related functions, so we can write the code that tests Fedora 36 in a very similar way to the way we test Fedora 37, for example. And when we want to introduce Fedora 38, which will probably happen in the next couple of weeks or so, we just have to change this file from saying 3637 to being 3738, now that 36's support has been dropped. It's also way easier to talk about or to implement cache busting, but I will talk more about that in a slide. So caching is key for performance CI/CD for us. Downloads and dependency compilation are really a pain point in the critical path of our CI/CD. And some of our dependencies, even on well-spec'd laptops, can take over an hour to compile. That's a huge pain point and makes it hard to do our longer, more LTS-style CI/CD things. Another thing that's potentially painful for us is what we would call stale caching. So if you've just used Docker files for trying to do these kinds of things before, you run into the problem where You built your Docker file, it cached a layer in your Docker file with all of your system dependencies, and then the system, whether it's DNF or apt, they updated the dependency, and now your thing no longer compiles because they changed an API, they changed ABI, and just stuff doesn't link. And you have a break in your CI/CD if someone were to run your code now, but if they were to have run it just a little while ago, they would not have seen that issue. There's also a few specific cases where you can get miscompilations or misconfigurations. These are somewhat rare and affect a very small number of packages that we don't build regularly. But these are potentially also things that we want to catch by strategically bursting our cache on a weekly basis. And then in addition to the Dagger cache, which is great and fantastic, we also use Dagger's ability to mount cache volumes inside of containers. We do that for the container-based images themselves, system packages from DNF and apt, so that we can share downloaded packages across several different containers. We do caching for artifacts downloaded for the SPAC package manager. And then we also use sccache/ccache. If you're not familiar with the C++ world, these are tools that allow you to partially cache the compilation of C++ codes to really speed up incremental compiles. Dagger makes integrating these things really, really easy. We use the with mounted cache thing in Python. It makes it really easy to do this. Cache bursting can very easily be done by date, so we can check by week. But soon we want to potentially implement this by dependency hash. I think there was a suggestion, can't remember who exactly made it in the Discord, but potentially we can ask DNF, what are the list of dependencies of this package based off the current state of the world? And then we can decide whether or not to break our cache based off what DNF says is the current list of dependencies. This has led to dramatic reductions in CI/CD time for us. Hot builds have gone from hours to a matter of minutes, and we can even, in some cases, get a lot faster than that. So I was running a test yesterday of one of our patch builds. The cold build took about 30 minutes, and then the hot build took less than 2. So dramatic improvements in CI/CD. Additionally, it's much easier to do improved parallelism. Dagger makes it easier to overlap downloads, configurations, and compilation using the mechanisms we're used to using in Python. So we can already just say, run these things asynchronously, and then we can use load averages, which is a mechanism within C++ style build tools to make sure that we're not exhausting our memory. It should be possible to do something called a job server FIFO using recent advances in GNU Make, and that's something that we'll look at doing in the near future. Other things that we would like to adapt within Dagger in the near future would be better coverage. So this would be integrating the stuff to test GPU-based codes, testing macOS and potentially Windows as those are available. We want to leverage the features that were rolled out in one of the more recent versions of Dagger to handle secrets, to deploy our docs to Google Pages, and to notify the various developers when builds fail in CI/CD. And then we want to potentially produce more artifacts and continue to look for ways to improve the performance of our CI/CD pipeline, distributing builds, implementing this shared Java server mechanism to better share resources between Dagger's various tasks. So in conclusion, Dagger radically simplifies and improves the CI/CD process for LibPressio by parallelism and caching, dramatically speeding up our builds, programmability, simplifying our builds, and portability, easing development and providing flexibility. At this time, I'll take any questions. And I want to acknowledge that LibPressio is a library that's supported by the US Exascale Computing Project.